Hello and welcome back to Precalculus1, section 3.5, the crown jewel of chapter 3. So the word problems that involve exponential models. In the intro to the whole thing, so these are all word problems, but in the intro, we first remember the exponential function. Which has the form of y equals a e to the k t. And we also remember the conversion, which was a to the b equals c, converts into log base a of c is equal to b. So these are the two things that we are going to need, and the rest is translating your word problems into equations and then calculating stuff. So we're going to start by first realizing the duality of the world around us. We have a growth and we have decay. So for growth, we have y equals a e to the k t, where k is larger than 0. And the graph for this would be our standard exponential graph that goes through this value a on the y-axis, so that's the y-intercept, and it grows in time. Maybe I should put not x but t, because it's time. You see, it's in exponent is t, it's not x. Now decay is y equals a e to the k t, but the k is negative. So you have a negative number there. And for decay problems, this graph obviously reflects on y-axis, and it looks like this. Again, we have a t-axis. We have t-axis. That's a. That's y. And that's it. So we have these two worlds. The world of growth and the world of decay. Observe that the function looks the same. It's k, the constant k, one that it's in exponent, which tells you whether you have the growth or you have decay. When k is positive, it's growth. When k is negative, it's decay. So for growth, we have money. You want to see money grow in account. And we have, let's say, population. So population growth. And on the decay side, we have loss of mass. We have, now loss of mass means radioactive decay, garbage decay, carbon C14 decay for carbon dating. So all of that stuff is there. And also metabolizing drugs in the system, in the body, right? You take a pill, it metabolizes in your bloodstream, so it takes time. So if I just write drugs, it's going to look bad. So I'll just write drugs. I don't care. Whatever. There we go. Drugs.
Medicine.
Medicine. There's way too many letters. Meds. I can recycle less. There we go. Better? So all of these problems will have the same base equation. And then we are going to use different letters to describe different situations. So the main equation is y equal a e to the kt1 that you see in 3.1. But then we have the money equation, which is that the amount is equal to the principal e to the kt. This is continuous compounding. Continuous compounding. We have the population equation, which is population in time is given as the initial population e to the kt. We have loss of mass, which would be m at any point in time is the initial mass e to the kt. So no matter which one of these you pick, right? No matter which one you pick, you will be using the same concept, same steps, same calculation, just using different letters because they describe what appears to us as a different application. But if you do carbon dating to discover how old an organic material that you dug up is, and if you calculate the radioactive decay after disaster or whatever, it's actually the same concept, same calculation, and that concept is loss of mass. So garbage decay, metabolizing drugs in a system, right, all of that stuff, like medication, all of that stuff is loss of mass, and it's governed by the same mathematical principle, which is this equation here. So now, moving on, I would like to discuss population, for instance. Population tends to be the cheapest thing to work with and to start with. And I will move to money. So population. We said that we have this equation that population in time is the initial population e to the kt. So this is population, this is initial population, and this is the growth rate. And for population which increases, that k needs to be positive in order to have k, to have a growth. We can use the real data for this and discover the process which this works. So what you see is the website, what you don't see yet, is the website called Population Clock, which is maintained by US Census, right, Bureau? And these are the numbers that approximate the population of the world and population of United States in real time. So as you can see, the US population is now at 326 million, and the world population is at 7.4 billion. And you have the top 10 countries there in terms of population: China #1, and then India, United States, Indonesia, Brazil, Pakistan, Nigeria, Bangladesh, Russia, and Japan, which is very interesting to see. Japan, it's just small, right? 4 islands crammed in a Pacific to have 126.5 million people. But anyway, what we can do is we can pick the data off of this website and come up with a mathematical model so that you can approximate the population of the world or United States in the future looking at the past cases. So if you have 2 points in time, you will be able to calculate the K for the model and the P0 as initial population, and then by plugging in different times, right, for the future, you can approximate the amount of people in the future. Now, my question to you is, would you like to do the US population or would you like to do the world population? Which one would you like to work on? We can do Japan as well, but US or world?
US.
I heard world 5. Okay, hand high up for US, touch the ceiling. US, touch the ceiling. And then world. All right, great, because at least 5 people said world, and then everyone voted for US. Great. All right. So we are going to use US data, and I need 2 points in time. So now means t is 0. And actually, yeah, t is 0. And we have 326.3 million. So I wrote down the first data point with the population now. Now this is, if you're reading this, this is t comma p, time in years. So 2017 is going to be 0 because we are saying now. So let's call that initial case. And then you have the population. And now let's find one old data point. So I'm going to Google US population in 1990, 2000, 2003. What should we pick? What year? 1999. So what we get for 19, actually, you know what? I'm not going to use 0 here. I'm going to use the 2017. That's this year. That's better. Use 2017. And then 1999 is going to be, according to Google search, 279 million. So we again have another data point. So this is also t comma p, right? So that's old and now. And let's say approximate population. And now give me the future year. 2030. So let me say approximate population in US in 2030. And that's what that's the goal. All right. So first of all, I don't want to work with these 1999 and 2017. What we can do is we can pick the smallest year and keep that as the initial case, and then count time from that point on. So set t equals 0 at year 1999. So set t equals 0 at year 1999. That means that my old point is now 0 to 79, and the now point is what? 18. Good. because between 2017 and 1999 are 18 years when you subtract them, right? So what we did is we just shifted the points, so we don't have to use the thousands for t. We get to play with 0 and 18 and so on. Now, crucial part, and I'm writing that here in blood over here. Here we go. Point with t equals 0 is called initial point. Now that means that the point, if you have a point with a 0, its initial point, that means that 279 million is our P0. So P0 equals 279. I am already getting my model, which is P of t is equal to P0 e to the kt. I already have 279 e to the kt because of the point that is initial point. So as soon as we pick the point with the lowest year, which is 1999, you pick that one as the initial, immediately you have the P0. So initial point is going to be 0, P0. So whatever has 0 for time is going to be your initial point, and then the number that you have for y is initial whatever, initial mass, initial population, initial amount of money, right? You go to a bank, you invest $1,000 and you wait. That $1,000 is the initial money you put in a bank account. It happens at time 0. You just open the account and you deposit that money. So that is now time 0. Everything begins from that point in time. So that's why it's called initial. And then you wait 1 year, 2 years, 5 years, 10 years, and so on. So that's where the calculation begins. Now that we have this much, we are still looking for k. K is going to be that growth rate. Now we have the second point. So now we use second point to calculate k. Well, second point has the population at 326.3, which is 279 e to the k times 18. So all I did is I plugged p for p, which is the population, and t for t, which is 18. We have to solve this equation. If you observe, the only variable that is unknown is k. So we can solve this equation. We divide both sides by 279. We use the same methods, except now your calculations are more annoying, so you will be using calculator all the time. And since this population, please make sure you round your final answer to the whole unit. Well, here we talk about millions, so yeah, you can have decimals. But if you're talking about single units, do not present your answer as, 19.7 humans, because 0.7 is not going to be a good division of a human. So if you're talking about whole units, right, you have to have whole units. Now, since we are dealing with millions of people, it's okay to have 13.7 million. All right, so the first order of business is to divide 326.3 by 279. And we have 1.2 1695. Remember I told you 4 decimal places. And this is equal to, leave some space, e to the 18k. Why do you leave space? Because you need to fit in the ln. So you are going to ln both sides. Compute the ln of previous answer, which should give you, again, 4 decimals, 0.1566. And on the other side, ln and e cancel. You know that this 18 jumps in front using the power rule from 3.3. So all you're left is 18k. Because ln of e is 1, and when you multiply, or you can say ln and e cancel, leaving 18k behind. Whatever way you want to work. And as you can see, you calculate k from here. K is equal to the number divided by 18, 0.00. Guys, these numbers don't count as significant. You can have 15 zeros here. It still doesn't count towards the decimals you keep. Now you keep 4 decimals. This in my calculator happened to be 8700, so we don't need to write those 2 zeros. But we need, this is a very bad example, unfortunately. You were supposed to keep 4 decimals here. It just so happened that it's like this, and I can't even round to 8701 or something. So you should keep 4 decimals after all of these zeros that are first. We'll do more examples, obviously. It's just on the first one, I don't want you memorizing you are keeping 4 decimals this way. Because sometimes those will all be zeros, and that's not how you keep significant figures. So you ignore, and now the decimals start 1, 2, 3, 4 spots. So that's the standard for our class. But we'll see more examples. Great, I have k. So now I have the population model. P in time is P0, which was 279 times e to the 0.0087t. This over here is the exponential model for US population. Robert, we're interested to know how many people, what is the population of US is going to be in 2030. Well, so population in 2030. So T is 2030 minus 1999, which is 31. And the population that we are looking for is when we plug in 31, which is 279 times e to the 0.0087 times 31. And now you plug all of this into your abacus, and you get the answer. The approximate population is going to be 365.4 million. So we went and used the exponential model to calculate the future. This is how you make predictions. And we can talk about money, we can talk about population, we can talk about whatever else. Those of you that are more interested in what's actually happening here, how all of this stuff works, we know that this is the initial population when we started measuring everything. Now, For the sake of argument and just thinking about this exponential model, let's forget that this is millions of US citizens, and let's say these are rabbits, right? It's easier. So we are starting a farm or something, right? And our initial population of rabbits is 279, so that's units, all right? Now, we can, let's say, wait a year and count number of rabbits in a year. And then that number will be hopefully higher. So you have your initial number of rabbits that you started with, which is 279, and let's say next year you have maybe 305 rabbits, whatever. You can calculate K. So let's say that this is something that approximates the amount of rabbits that you will have at any future time. See, when you see exponential model, you immediately locate two pieces of information. One is the initial state, so this is the amount of rabbits that you're starting from, and this number here being positive means that over time the population of rabbits will increase because it's a positive number. Now, you might say, well, if we start with 279 rabbits, but they're all female, the population is not going to change up, right? Because you need both male and female rabbits to have increase in population. Well, if you put 279 female rabbits in whatever, on the farm, this K will automatically turn to 0. Because you just have a constant 279 rabbits. They can't increase their population. Obviously, if you stay, oh, but they will be dying, well, in that case, yeah, it's going to be negative because population will decrease. But let's say that these are 279 female immortal rabbits. So you can't kill them, right? Or anything. So in that case, if they're all female, this immediately becomes 0. This number K encodes a lot of stuff. Food, right? And then their sexes, ratio of sexes as well, the predators, right? The environment, disease and sickness and everything else. All of those factors that are there and impact the change of population, for better or for worse, are together encoded in this. So now, when you are looking at the population of the United States, if we say that we have the 279 million Americans, right, that K of 0.0087 takes into consideration everything which impacts the change in number of population. The birth rate is encoded in it. The death rate is encoded in it, right? The retarded gun laws we have is encoded in that as well. Everything that we do, and in terms of population change, is encoded in that number. And the only way I get to change this K is to look at a different point in time to calculate that K, but then this number changes, that number changes, and then everything else changes. But you should get approximately same value if you look at 2030. So this is the reason why these approximations are so hard to do. But our calculation, I hope you appreciate, a very systematic way to get this. You must have 2 points in time, and this is going to go for everything technically. So you must have 2 points in time, so you are able to calculate things. You zero out the lowest point, so we say the time is 0 at 1999. then scale the other one to 18, right? Whatever had a 0 in it is the initial population, so that's your P0. You start at that population. You already have your half of mathematical model here because P0 is there and you need K. You will use the other point to plug in population P and time T, because you have T comma P, 18 and 300, whatever. You plug those numbers, then you use your 3.4 to solve it. So ln both sides, right, to get rid of E, what we did last class on Thursday. These guys, you can either say these guys cancel and you get 18K, or you can say 18K jumps down from the power rule, and then ln of E is 1, right? So whatever way. And then you have your mathematical model. Once you have this mathematical model, you can go anywhere in the future for it. So you can ask about 2019, 2020, 2050, whatever. You just need to make sure that you are scaling the numbers down to the values that we have to plug in. So 31, since we are counting that the beginning of time is 1999, then 2030 is going to be 31 years away from that time. So you have to plug in 31 to get the number of people in 2030, and so on. So you have to do that scaling as well. And those are the population things. Now, we can look at, let's look at money. So we're talking about loans. Now, for loans, you have the equation with E, which you can use to quickly approximate the worst possible case. And then you have actual models that are used. So, two models that we are talking about are amount is equal principal E times the RT instead of K is R for rate. We have the amount principal and the rate in percent written as a decimal and time in years. So amount, principal, rate as decimal, and then time in years, which means 6 months is 1/2. So be careful about those problems, right? 1 month is 1/12, 2 months is 1/6, and so on. So the time is given in years when we talk about these money problems. So this is over here, continuous compounding, and we'll talk about that. You all know about the interest and stuff, so that's what we're talking about. But the one formula, which you've probably seen already a few times in your homework and you were wondering what the hell is going on, is the amount is equal to 1 plus R over N to the NT. This is called compounding formula. And this compounding is done to this value n, where n is the number of compounds per year and then you go, what the hell is compound? Compound means calculations to add interest. So we start by understanding that interest, when you take a loan, is a service fee. That's how banksters make money. I like to call banksters because it sounds more like gangsters than, bankers is somehow like a mundane term. I don't like it. See, when you go to a mechanic to fix your car, you pay for the part, but you also pay for labor. When you go and rent a room in a hotel, you pay for the room. And that works everywhere, right? Except if you go to ShopRite or one of these stores today, you actually go there, you pick the stuff, and then you go, you check it out, and then you pay and leave, which is right for the self-checkout, which makes no sense. But most of the time, you pay, right, for services and goods. When you take a loan, let's say $2,000, there is interest on that loan. And that interest is the service fee. So that is what someone gets as a payment for the services of lending you money. So you don't have $20,000 to buy a car. Bank says, we do. We just want 3%, right, to give us, right? And then they give you $20,000. You go, you buy the car, and then you return $20,000 plus 3%. That 3% is what bank makes as a profit, as a service, because they lend you $20,000, let's say, over 3 or 4 years. Now, these formulas compute that. Oh, I forgot to put the P. Whoa, hold on. There's a P over here. Guys, principal has to be there. So this A is the final amount that you have to pay back. Principal P is the amount you borrowed. So if you are borrowing $20K to buy a car, that goes for P, that's the principal. Let's say you borrowed at 3%, so that's 0.03 over here. And since you will be paying monthly, N is 12. On how many years? 5, 3, 7. That goes for T. So 12 times 5 would be 60 up there. 60 payments. So let's buy a car. Let's go with 20K. So let's say car is $20,000. No down payment at 3% for what amount of years? 5 years. This is a calculation that you can do while still in pajamas and not bothering going to the dealership. Great. Now, you just know, this is just by being alive, you know that year has 12 months and you will be making 12 payments, which says N equals 12. So compounding in the problem generally says monthly, which means N is 12 because you pay once a month. But there's also quarterly, right? That's 4 times a year. N is 4. There's annually 1 payment a year, right? Which is a tax, right? You pay taxes once a year, annually. So N is 1. So there is weekly, 52 weeks, bi-weekly, 26 weeks. So this N can be any of these numbers. But then N could also be infinity. And if N is infinity, which is called continuous compounding, you learned that better in calculus, then it's this formula here. And that formula gives you the worst possible case, because it calculates interest rate at all points in time. This one calculates interest 12 times a year if you're talking about credit cards, car loans, or any kind of school loans, whatever loans you take that you pay every month. I told you that the mortgage doesn't fit in that formula because mortgage does some crazy stuff. There are formulas for mortgage, it's not arbitrary, but other loans fall into this formula. So let's get this car. What I'm going to ignore are the extra fees that you actually pay when you get there. When you are buying a 20K car, there is a tax on 20K car, which is $1,400, right? So there is plus $1,400 for the tax. There is plus the title and the first few week insurance before your insurance kicks in. There is this fee and that fee and all of the other stuff that they tag on. So if you're buying a 20K car, you probably add at least $2,000 or $3,000 in fees and taxes on top of the sticker price. And that also has to come out of your pocket. So you will not be using 20K as a principal. You will be using 23K as a principal. But for the simplicity, right, for this problem, let's just ignore all of the taxes and all of that stuff. Let's hide some taxes here, right? Let's just use 20K as that's the money that you need. So amount is going to be 20K, 1 plus 0.03, that's 3%, divided by 12, raised to the 12 times 5. So I ignore the tax and everything else. And now you calculate, so this is something that you can punch in a calculator in one shot, right, using parentheses if you're using 83 or 84, and get the answer in one shot. Make sure that you are rounding 2 decimals for cents. Don't give me 17 decimals there, because cents are just 2 decimal places. So we go with 20K, open parenthesis, 1 plus 0.03 divided by 12, closed parenthesis, caret, 60. Because you can do 5 times 12 in your head. And you get the amount that you owe. So A is equal to $23,232.34. Owe back. That's what you owe back. So you borrow 20K, you owe back 23K. So what is the difference? The difference is the interest. That is what bank makes because you didn't have 20K cash. If you walk in a store with a 20K cash, right, duffel bag or something, put it over there, then your car is 20K. But if you walk with a, the pockets like this, then you have additional $3,000 in fees over 5 years. Now, from this point on, you know how much you owe back. You can divide that payments, right? Because you will be paying back monthly, and you can calculate your monthly payment, MPT, monthly payment, of $23,232.34 divided by 60. Yep. 387.21. Perfect. So that's your monthly payment for the car. If you did this at home and you say, I can't put this in my budget, well, guess what? You don't go to the dealership and waste gas and waste time. But let's say you did. Let's say you didn't do this calculation, didn't care, you're just gonna go. You really like that red car. Red is a nice color, it stands out on the highway, you get pulled over at a high rate. So, right? You have a red car? Smart. Anyone with a red car? No? Oh yeah? Oh. So now, let's say you went to the dealership and the dealer says, well, it's $387.21 a month. You say, there's no way I can pay that. I don't want a car. What's the first thing they say? Exactly. No, wait. Hold on. If you finance this thing over 7 years, the payment goes down. The same trick what they do for refinancing or a house, except it's much draconian difference there. So you go and you say, all right, so now what I have is the option 2. Same 20K to borrow, 3% interest, but now 7 years. The monthly payment will go down. This is how they sell the cars, right? But we'll discover something else. Believe it or not, they can't wait for you to say, no, I can't do this. They can't wait. Let's see why. You're borrowing 20K again. It is 1 plus, and you have 0.0. That doesn't change. At 12 months still. But now it's 12 times 7 for 60, for 84, right? 84 payments. So clearly, if you have 60 payments and if you have 84 payments, right, you have more payments, it has to go down. So let's punch these numbers in the calculator, see what we get. So 20K, open parenthesis, 1 plus 0.03 divided by 12, raised to, and then 12 times 7 is 84. So amount is 24667 and 10 cents, and the monthly payment dividing by 84 now is less than 300 bucks. Yay! 293.66 cents. So, wow! It's $90 less a month. Is this great? No. Why is this not great? Oh, you see it right there. You get to pay $1,400 extra over time. Who gets to make that money? Yeah, you do. It goes out of your pocket. So that game of, yeah, just, you know, and don't worry about it, it doesn't work. If you know the formula, right there, you can see that over time, your payment, they don't give you this number ever. You go to buy the car, they will never ever mention that number. They just say, this is the monthly stuff. This is how much you pay monthly. Don't worry about it. Just you know, if we just move it across, right, completely hiding the fact that you will be paying $1,500 more over time. Because obviously, you are compounding extra 24 payments of interest that are added into calculations over time. So, you have to be educated on these kind of things, right? To see through those schemes, and then if you can't afford $387 car, well, you can't afford it. And if you force it over a long time, you're locking yourself into extra 2 years, what you didn't plan for, and you are also dishing out additional $1,500 out of your pocket. Now, this is like 5,000, 100,000 times worse if you refinance a house from 30-year loan to a 30-year loan. It just, you practically lose all of the money you paid in up to that point of refinancing, and then you're technically starting from zero. So this is what we have for these calculations. Now, your school loans are going to work the same way. The credit card is going to work the same way. Credit card also has this compounding on 12 because it's a monthly payment. Loans for whatever stuff you take, loans, so school loans, they're all 12, right? Because of the 12 payments per year. Now, you can also calculate the worst case scenario by computing the exponential one, where you go and you say, my car is 20K. Right? This is very quick. You don't have to go to the formula up there. This one gives you the worst case scenario, and you just say, okay, the actual car payment will be a little bit less. And I want to show you this. So at 3% for 5 years, you just plug all of that into amount is equal to 20K e to the 0.03 times 5. It will give you the larger number than we had earlier. But it's not going to be that much larger. And this is the worst case. Can't go worse than this. So as you can see, it's only $4 difference almost. Used to be 232 and now it's 236. If you go with 20,000 at 3% for 7 years, you will have approximately same number as before. So going from 24,667 to 24,673. So yeah, within $10, right? So this is the fastest way for you to figure out whether you can buy a car or not if you have nothing for down payment and all of that stuff. You go and just do this compounding. The other formula is the formula that's actually used. So the other formula is exact. But it's going to be exact only if you plug in the tax on the car. Right? So you're buying a 20K car, it's going to be $1,400 tax. And then all the other fees included on top. And then that's the money that you borrow. Not 20K, but maybe 23K. Which obviously will push this into 26 or 27K that you need to return. So these are the calculations. Now, you took a $4,000 loan to buy whatever, the whole new furnace at home, computers, fridge, whatever. Any loan you take, right? And then whatever you charge on the credit card. You turn that paper when you sign the contract in the credit card, it then tells you the percent. That's the interest. Your credit cards, right, that you're just starting out, should be about 23, 24%, right? And then scale it down to 16 and so on as you are developing good credit along the way. So these are the calculations, these are the money calculations that you see from these formulas, and then you can compute these things. Now, I have another interesting calculation. How long will it take to double the investment at 3% interest? So technically, you are now in a position of making money. You invest $1,000 at 3%, and the question is, how long do you have to wait for that $1,000 to double? Well, and use the continuous compounding for ease of calculations, right? So let's, I'll just say continuous compounding. Right, so we know that the formula is amount is equal to principal e to the rate times time. How would you set up this problem? If I say how long, what are we looking for? We are looking for t. Good. We don't know how much we're investing, but we know we're looking for t. Good. So t is the question mark. Now, what else do we have as information? Rate. So r is 0.03. Same like in our car example. That could be any number there. And then what else do we have as information? Aha, you want to double. What are you doubling? P. And where should that go? For what variable? The double P, the amount. So this amount should be 2P. This stays as P because we are investing some unknown quantity. But we want to get 2P out. So whatever I put for P, I need to get 2P on the other end. So this problem sets up as 2P is equal to P e to the 0.03T. Do we all see that if we divide both sides by P, they drop? Right? When you divide by P. And now your equation is 2 equals, leave some space, E, 0.03T. How do we solve this equation? ln both sides, nice. ln will kill that T, right? On the right hand side we have ln of 2, 0.6931, there are the 4 decimals we talked about, is equal to 0.03T. Multiply both, divide both sides by 0.03, and we get T equals 23.1 years, so 23 years and something like that. So how long does it take to double your investment at 3%? 23 years. It will take 23 years to double the investment. Now, what's the investment? How much did you invest? The question is, actually, does it matter how much we invested? Look at the calculation. What happened with P? It canceled. When that happens in mathematics, it means it doesn't matter. You see what crazy thing over here is that if you invest $1, you have to wait 23 years to become $2. If you invest $1 million, you wait 23 years to get another $1 million. You see that? You ever heard of that thing, who has money makes money? So if one person goes and puts $1, in 23 years, that person will have $2. And another person goes in and puts $1 million in the same amount of time, that person will have $2 million. So it matters what you put in, not just how long you get to wait. Now, this problem can be done to triple the investment, to quadruple the investment. That just changes 2P, 3P, 4P, whatever. That P will always cancel because it doesn't matter the amount you plug in. What matters is the percent. And banks know how to play the game. If you go there to ask for a loan for the car, They tell you, we are lending you money at 3%. Now, where the bank gets the money? Well, you got in, and you got in, and you got in, and you put your savings money in, right? And they said, we'll give you 1.8%, 2%, right? 2%, 2.3%, right? Better than the one across the street. So you go there, you put $1,000, they give you 2.3, but then you don't have 20K. You borrow from them 20K, because if everyone in this classroom puts in 1,000 in the bank, they have 20,000 liquid money, right, which they can use. So they collect 1,000 from everyone and promise to give 1.8 or 2%, right, interest back. So you will make money over time. But then one person comes in and says, I need 20K. And go, here's your 20K, but I want 3% back. You see that? So I took your money and I invested that money at higher rate. And then when the higher rate came back, I paid you all your little percents, right? Because the percent what I got was bigger, right? And I constantly make money. No matter if I borrow or if I lend, it doesn't matter. I always make money. That's the bank's position at all times, right? The biggest scam of the century. They always make money, no matter what. They make money. And if you want to pay, well, they come in and they collect your house and your kids, and that's it. Kids are worth more than the white market in the house. Or they take a kid. Whatever works for them. So there you go. That's the money. You have the equation. You are considering a loan. You calculate, and then you know the monthly payment, and then you decide whether that loan is good for you or not. The lower the percent when you are borrowing money, the better. The higher the percent when you put the money into the bank or a bond or something is better. In a good old time, it used to be 9, 10%, right? Now, hey, you can find 1.7. It's like insane. It's like, ooh. Right? So, yeah. That's money. Is it time to talk about decay? Do we have any others? So population and money, those are both growth models. We cover the compounding, continuous compounding, and population. Let's do some decay. Meaning k less than 0. Negative k's. All right, so in this segment, we start the talk with defining half-life. Half-life, which is denoted by Greek letter lambda, is the video game published by Valve. I'm just kidding. So half-life is the time in which half of the original mass is lost. So, you have something that it's 1 pound, and it is going to radioactively decay, or decay with the help of worms, whatever. It's going to go away. Half-life is the time in which this 1 pound of stuff goes down to half a pound. Now, for radioactive elements, if you have a 1 pound of stuff, you might have to wait 1,000 years for that 1 pound to go down to half a pound. E equals mc squared. Mass and energy are the different aspects of the same thing. If you want to go study advanced physics, you can, but the mass does gets converted to energy and radiates away, and your 1 pound after number of years 1,000, 2, 3, 5, 10,000 goes away. Half-life for a plastic bag from your favorite retail place, 10,000 years. Now, does it mean that in 20,000 years that plastic bag is gone? No. In 20,000 years, you are going to lose a quarter. And then 30,000 years, additional 8. Because anytime you do the half, the remaining half gets cut in half. And then the remaining half gets cut in half. And the remaining half gets cut in half. Stuff doesn't go away. Nothing gets to go to decay to 0 because it's exponential graph. Remember, when I'm talking about a mass on a decay problem, it's going to look like this. This is your initial mass m0, and this is your time. So if this is the mass axis, observe that the mass is decreasing, but it's not hitting the 0 level. Okay? So if you have 100 pounds of plastic, and it takes 10,000 years to lose half, so lambda is 10,000, so that means that 10,000 years later, you have 50 pounds, and then if you wait another 10,000 years, so now it's 20,000 years later, you will have 25 pounds left. And then you wait another 10,000 years, which is a half-life, so now you're at 30,000 years of waiting. You have 12.5 pounds left. And you keep cutting in half what's left, because every 10,000 years you lose half of whatever you have at that moment. That's exponential decay. You don't go 10,000 and then 10,000 for the other half, you're gone. No. You go half of the remaining amount every time. So how long do you have to wait for 100 pounds or just one plastic bag to decay? Infinitely long. That's how, in infinity, it's going to equal to 0. So now that we have a concept of half-life, we can talk about radioactive decay, we can talk about carbon decay, C14 isotope of carbon, so that we can do carbon dating. It's very popular in archaeology, right, to dig up a bone, which was organic material. Then you take a sample of that bone and you run the amount of carbon, C14, that it's present. There is a certain percent of it, and then you can figure out the time, how old that bone fragment is. You can do that with paintings, old paintings, like from Da Vinci's time and so on, the Renaissance. All of the paintings, all of the paints were organic, based on flowers. So you scrape a little smidgen of the paint, not obviously from the middle of the painting, but from the back somewhere. And again, carbon C14, you run the equation, you figure out how old the painting is. Goes for the old scrolls that are made on papyrus, right, which is made out of trees, and so on. You can't carbon date the stone, so you can't go and carbon date the pyramid. That would be dumb, because it's not made out of organic materials. What you can do is you can dig around and hopefully find a grave, and then take the bone, and then you try to figure out and extrapolate how old the damn thing would be. So half-life is going to be the time in which the half of the mass is lost due to decay. Now, you can go and take a look at the nuclear site, whether it's Chernobyl, right, or whatever, where the nuclear leak happened. And you can calculate, we know what are the acceptable doses of radiation are for humans to survive in those conditions. So you can calculate how long would it take for radiation to go down to the levels that are acceptable. You have the measurement, which is the present time. You have the target measurement, which is where you want to be, and then you can calculate the rest. You also have the half-life and everything else. So let's take a look at one of these. We can take a look at uranium, for instance. Uranium is usually used to fuel the power plants and nuclear weapons and stuff like that. So uranium would be one of the fuels that we use now. The smidgen of uranium, that much, is powering nuclear submarine for like 20 years or 30 years. There's no refueling time or something. You just send it and it's just going to go forever and ever and ever. So now let's take a look at uranium. Yeah, 235, I guess. And I want to know its half-life. Great. All right. So 235 U, that's the chemical symbol in the periodic table. And we have the half-life of 703,800 and then 3 zeros, years. Huh? Good one. So this means that you have to wait 703.8 million years to see 1 pound of uranium decay to half a pound of uranium. And then another 703.8 million years to see that half decay to a quarter. And go on like that over and over and over again. So let's say, so how long do we have to wait for 3.6 pounds of uranium to decay to 70% of its initial mass. All right, that's a fair question. We start with the mass at any time is the initial mass, right, M0, E to the KT. And we can use the half-life. So half-life occurs at half of the initial mass and the, I had half-life and half of the initial mass. So that's when the half-life occurs. So we plug this in, so M0 divided by 2 is equal to M0 E to the K lambda. And you see that these M0s cancel, which means that it doesn't matter how much uranium or whatever you're starting with. Doesn't matter. You will ln both sides, so you have ln of 1/2 is equal to ln E K lambda, from where ln 1/2 is equal to K lambda, and there's your equation for K. It's 1 over lambda times ln of 1/2. Right? If you divide both sides by lambda or multiply by 1 over lambda to get k alone, because that's what we are interested in. We're interested in k. Once we have k, we have a mathematical model. We can calculate whatever the hell we want. All right. So now I can use the equation for k, which is 1 over 703 800 times, I'll just put ln of 1/2 on top. It's fine. This is going to be insanely tiny numbers, so we have to use scientific notation here. We have ln of 0.5, close parenthesis, divided by 703. I think this is good enough. 1, 2, 1, 2, 3. Yes. Boom. So k is negative 9.849 times 10 to the negative 10. It's a ridiculously small number. And we have our model for decay of uranium, which says mass at any time is the initial mass E to the negative 9.849 times 10 to the negative 10 T. So this is the model for decay of uranium. What do we want to calculate? We know that we are starting with, what did I say, 6 point something? 3.6 pounds. E to the negative 9.849 times 10 to the negative 10 T. We have to calculate the time. And we want the 70% left. So that's 70%, so that's 0.7 of 3.6. Now observe that this 3.6 is irrelevant, actually. We didn't actually have to have that piece of information at all. Just like you didn't have to have money what you invested, because you canceled. But for the sake of the first problem, let's put it in. So 3.6 pounds, scale down to 70%, what you want to stay behind. And the 3.6 will cancel on both sides, and the T is the only variable you will calculate using ln, obviously. So we have ln of 0.7 is equal to ln E negative 9.849 times 10 to the negative 10 T. All right, ln of 0.7 is negative 0.3567 is equal to negative 9.849 times 10 to the negative 10 T. Just divide by this number and we have T. So T equals our whole number divided by negative 9.849 to the negative 10, and the answer is 3307.9 years. So you have to wait 362 million years for the sample of uranium to decay to 70% of its original mass. It doesn't matter if you start with 1 pound or 10 pounds or 1 gram of it. You have to wait this long for whatever amount you started to lose 30% and stay at 70%. Cool, right? We have time for one more example. So let's do the carbon dating. And then we'll do more of these examples when you come back. I hope that you will, over the break, try a lot of these and bring in the questions. Our next class, which is on Tuesday. And I will actually do at least 2 more examples of my own accord. Right? So there will be a part 2 of this lecture. Let's do the carbon dating problem with, let's see what we have. I still have to do the medical application. I have to talk about population again and other things, so there will be a part 2 of this lecture. Newton's law of cooling, so yeah, we have a lot to cover. But let's get some of the basic problems out of the way, at least. So use the exponential decay model. This is problem 20, let's say. Exponential decay problem, A equals A0 e to the negative 0.000121t. Model for C14, that's a carbon isotope. Skeletons were found at a construction site in San Francisco in 1989. And the skeletons contained 88% of carbon C14. How old are remains? So skeletons were found. We know that skeletons are consisted of bones, and bones are organic material. So you can see the amount of carbon C14. It turns out that 88% is present, which we have the model, we can compute. I don't like that they use A. I should use M for mass, but yeah. I guess amount of carbon C14. Hey. So what's left? We have 88%, so 0.88 of original amount is equal to the original amount e to the negative 0.000121t. So I'm replacing A with 88% of initial value, because that's what I have. Now the initial value, when you divide both sides by A0, will drop. We ln both sides. It's the same calculation over and over and over and over and over and over and over again. So ln E drops. We have ln of 0.88, which is negative 0.1278 is equal to negative 0.000121t. Divide. $1,056.5 years. So the skeleton remains. Skeleton remains are 1,056.5 years old. Now you can work out that from 1989, right? So it would be 1989 minus 1,000, right? 56 to find the year, and then you try to figure out how old does the skeleton appears to be, right? Is it a child, is it mid-age, right? They can do that somehow. We can subtract that to the birth, approximate the birth year or something like that. So these are the carbon dating problems. Now, we did not use lambda because the equation was pre-made for us. We would have to use that procedure with k equals 1 over lambda ln half to figure out this number. So they either give you the model or they give you lambda. If they give you a model, you don't have to calculate this. You have it. But if the lambda is given, the half-life, if the lambda is given, then you have to use the formula to calculate k first, then you have the model, then you go and you compute the rest to come up with the time of how old something is. Well, that was a very quick example. Should we do another one? No? What? What holidays?
Thanksgiving is one holiday.
That's not even out. It's just stupid. Holiday, the meal. Let's go have a big meal. Once a year. So one day when I just, out of spite, look at me. Thanksgiving is all right then. Part 2 of this lecture on Tuesday. We are going to look at some spicier examples. So see you in a week.